definitely get through the first three, and we may end up with a little bit of the next one. So Canvas, is anybody on Canvas? So you said you can see it now? Okay, all right. I'll be super careful about that, I promise. Because you have to publish every little thing, and sometimes, I don't know, sometimes you don't see that button, so I'll be careful about that. Okay, so on 1.3, this is actually a fairly long section, it's got a lot of things on it. We're going to kind of breeze through the first part of this. And this is stuff, a lot of you have had calculus before. If you have had calculus before, you know, this is something you work a lot with in calculus. So we're going to look at functions and when they're increasing and decreasing, okay, and learn how to write that, okay? Basically what happens on this, and I'm going to go through the definition. The definition's technical, but it's not that hard to learn, really. The idea is increasing from left to right, what's happening to y. Y is getting bigger, okay? That's what increasing means. And if you look at your definition of increasing, the number one thing you want to pay attention to is open interval. What does that mean? It means parentheses. So if you're naming an interval where a function's increasing, you're going to use parentheses in that interval. Okay, by definition, it's open. Now what it basically says is if you have an x value, let's say that's x1, and that's x2. If x1 is smaller than x2, then that means that the function value is going to be smaller than the other function value. Does that make any sense to you? If this x is smaller than that, and this y is smaller than that, then it's increasing. That's the technical definition. So increasing is pretty easy for a student to see. It just means the y values are getting bigger as you go left to right. Decreasing is the same thing. If you look at this definition, it says if x1 is less than x2, then the function values are in an opposite order like that. Constant, what does constant mean? It means just the y values stay the same. So those are the possibilities, but be sure you pay attention to the open interval anytime that you name these intervals in. So that's the idea, okay? All right, so let's, on this example, I'm going to just run through, and you can just write this on paper for today, and that's okay. So it looks like we have -3 here, and we have 1 here, and then we have 4 here. So what we're going to do is we're going to name where it's increasing, where it's decreasing, and where it's constant. Okay, and again, we're going to do open intervals on this. So let's just kind of start at the left, and what do we have? So what's it doing here? Increasing. Increasing. Now it hits a high point. Now what it's doing? Decreasing. Decreasing. It's a low point. Then what? Increasing. Increasing. Then what? Constant. Okay, so it's real easy to see that. So just name your intervals like this. Increasing would be this and this. It would be those two areas. So we would just say -infinity to -3. And then we would say union. Usually you put union to unite the other interval. Then it would be 1 to 4. Okay, like that. Okay, decreasing would be the area I'm shading in the blue. So that would be just from -3 to 1 with parentheses. And then constant, what would you put on constant? 4 and then forever. Okay, so you would say 4 to infinity like that. Okay, now most of you are going to take calculus like next semester, so you'll do this all the time in calculus. You'll, do derivatives and things like that, so you want to be solid with how you write your intervals in this class, okay, and get the idea what that is. Any questions on that? Okay, next thing what we're going to do on this, and I'm just going to start with a couple of graphs. So what I want you to do on this number 2, go ahead on this one, and you can just write the answer down on a piece of paper if you want to. You don't necessarily have to draw the graph out. Just take a minute and see if you can get the answer on that. Okay, just write your intervals and remember they're open intervals. So you'll do that, and then we'll do one more together. Okay. Any questions anybody has? Okay. Just write down how your intervals go on that, and then we'll look at one more. And remember, they're always open. Always use open intervals, so always use parentheses. Okay, never a bracket, ever anywhere on these. Okay. So let's see. Increasing, it looks like from there to there, there to there, and there to there. So there's 3 basic intervals where that's happening. So it looks like this is what? 1, 2, 3, 4, negative 5 there. That's negative 1, that's 1 there, and then this is 2, 3, 4, like that. So it looks like what you'd have for increasing is negative 5 to negative 3, then negative 1 to 1, and then finally it would be, what, 4 to 5. Okay, like that. Okay, decreasing would be here and there. So you need to name those in intervals. So the intervals on that would be negative infinity to negative 5, and then union 1 to 4 like that. Okay, constant just means it's flat. So constant would be here and there. So that looks like negative 3 to negative 1, and then 5 to infinity. So that's what you have. Okay, everybody got that? Okay, students usually don't have any trouble with this. It's pretty easy to see what's meant by that. So that's what we mean by increasing and decreasing. Okay. Now this next graph, I'm going to kind of do the same thing. Let's just do this together, the same idea. So look on the increasing. The increasing just means the graph's getting bigger from left to right, so it would go like this, and then it would go like that. Everything's open. You don't really need to pay attention to the open bubbles and solid on this. So what we would say increasing would be 0 to 1, union, and then 2 to infinity like that. Okay? And let's see, as far as decreasing, the only place I see decreasing is what I'm highlighting in blue. So that would be negative infinity to 0. And then finally, constant would just be this area here. So that would be 1 to 2. Open intervals. Just remember that. That's the thing I see students forget a lot of times on this. All right. Everybody okay with that? Okay. All right. That shouldn't be that bad of a deal. And if you took calculus, a lot of you did that. You've seen this before. If you took pre-calc in high school, you would have seen that. So the next thing I want to talk about, this is a calculus idea. Since it's pre-calculus, we introduce you to the ideas that you'll see more in depth in a calculus class. All right, so what a local or relative max is, you'll hear me use both terminologies. Calculus textbooks usually use one or the other, but they're interchangeable. They mean the same thing. So what a relative minimum really is, or what a relative max is, it just means that what you're going to have is, when you have a max, the easiest way to think of this is, number one, it has to be a point. Okay, so if it's a bubble and it's not defined there, then it's not a maximum or a minimum. Okay, the other thing is, when you have a maximum, what does the function do? It increases, then it hits a high point, then it starts decreasing. So one of the things you want to get settled on this is, look for a point, and that must be a point, where this happens. So there has to be something on the left and something on the right. So if you look at this particular thing right here, that would not be a relative maximum. How come? Because it's not even a point, right? Okay, that's not a maximum. Even though it increases and decreases, that wouldn't count, okay? Same thing there. Now, if that's an open dot, it wouldn't be a minimum. But what a minimum does is it decreases and then it increases like that. So it's the opposite. Does that make sense? It can't be an endpoint or anything, but you always have to have something happening on the left and right. So one thing that you might write down, I'd recommend you write this down, is that an endpoint of a graph, an endpoint is not a relative max or min. It can be what we call an absolute max or min, but not relative, because there has to be something going on to the left and right. Does that make any sense to you? Okay, yeah.
So what did you mean by 0, 0 is not a point?
Okay, this one, it looks like on my graph that's a bubble. Okay. So that means it's undefined there. So you would not be a maximum. It has to be a point, and the thing, here's why. If you are barely to the left of 0, then you couldn't pinpoint that y value down. It's going to get closer and closer to a y value of 0, but it's never going to hit it. Does that make sense to you? It's not a point. It's got to be a point, and then this has to happen. Okay? That's what we mean by that. So at this next diagram here, now this would be what you're looking for. So a relative max, that's a point. You increase, you decrease. Okay? That's a relative min. You decrease, then you increase, and so forth. That's what it means. So you would have 2 relative maxes there and 2 relative mins there. Everybody with me there? Okay? Make sure it's a point, not something that's undefined. That's important. Okay? And then this, I told you to write this down, but I guess I put it on there for you, endpoints are not local max or min. So if you look at this diagram here, this would be a max. This would also be a max. And then this would be a min like that. Okay? But the endpoints don't count. Everybody got that? Okay. All right, any questions? Okay.
You can have more than one max.
Oh, yeah. Yeah, and see, all that relative means is in a small area of the graph, you have it hitting a high point. Okay, you can have a whole bunch of them. You can have lots of them, yeah.
Does one side of the graph have a point and then the other have an endpoint?
Yes.
What would be the max?
Okay, so like you're saying, like what? You have, what, an endpoint? Something like that?
Yeah.
Now, what do you want over here? Just going on forever?
An endpoint.
An endpoint like that.
Yeah.
Yeah, you could have that, and in this case, what you would have is relative max there, relative min there. But those don't count. Okay? That's what it means. Now, see this? That's the high point, right? We're going to call that an absolute max, but not relative. Relative, you always got to have something happening to the left and something happening to the right of it. So an endpoint doesn't count. Everybody got that? Okay, so it's a little picky deal about the definition. Okay? All right, now here's what absolute is. So this will, hopefully this diagram will kind of clarify everything. So an absolute max just means that you hit, that's the highest point the graph ever hits. Now this point right here is both an absolute and a relative. It's a relative because it increases then decreases, but it's also the highest y value it ever hits. Okay? This point right here would not be a relative because it's an endpoint, right? But it would be absolute minimum because that's the lowest point the graph ever hits. Does that make sense? Okay? So again, you've got relative max, relative min, relative max there, and the endpoints that would only count as an absolute min. That's it. Yeah.
So anytime your y value changes from increasing to decreasing or decreasing to increasing, you have
exactly
relative max or min.
Yeah, that's it. So a max just means you increase at a high point and then decrease. Minimum is decrease then increase. That's all it is. Okay, and that's why endpoints don't count, because there's nothing happening on the other side of it. Okay, the graph has to change directions. Okay, let's see. Let's go to this and let's kind of take a look at a couple of these right here then. Okay, so let's just kind of do this together. You can kind of look at my graph and we can write this together. First of all, how many local minimums do you see on this problem? Local minimum, how many? One. Where is that local minimum? Yeah, okay. It's going to be a place where the graph decreases and increases. So that's it. Okay? Yeah.
Now, would you call that by 0, -4?
You would just say the point 0, -4. That's what we're going to do. Okay, how many relative maximums does it have? That's 2. What are they? -1 and 3.5 maybe? Okay, I'm kind of seeing that as 3.5. Okay, that's it. So what you would end up having is local minimum would be here. So that's a local min. And you can just say on that the point 0, -4. Okay. I usually just have you name them with points. Local max would be here. And that would be the point, we'll just say 3.54. It looks like what that is. Okay. Now, what do you think the absolute minimum is? There isn't one. How come? Because it gets lower forever. Okay, so there is not one there. How about the absolute max? Does this reach a high point? Yeah, this right here. This point right here would also be the absolute max. So it can be both. So this would be the same thing. It would be 3.54 like that. Okay, that's it.
For the purpose of these questions, we're assuming that never comes back up. It's down forever.
No, because the endpoints, if they have an arrow, that will tell you the tendency from there on out. Okay, those arrows are kind of important. They tell you you don't have endpoints. Okay, all right, let's look at this one here. Okay, how many local minimums? There's one. There's one place where the function decreases then increases. So that would be the point 0, 0. Okay, how many local maxima? How many? 2, good, okay? Local max would be here and there, okay? So that looks like that would be, what, negative 216. You'd have this point, negative 216, and then you'd have 216 like that. Okay, how about absolute minimum? Does this have an absolute minimum? Yeah, it has an absolute low point because that's an endpoint. So it looks like that's 10 below like that, negative 10. So that looks like the absolute minimum is at the point 3, negative 10. Okay, and then how about absolute max? Yeah, there's 2. It's the same value, but you need to list both of them. So you would have negative 216, and then you would also have to list 216 like that. So that's it, okay? That's the idea. So it's really 2 points reach that high point like that, okay? All right, let's take a look at one more of these, just kind of get the idea. So if you were looking at this one would have a local maximum there. That right there would be a local maximum, okay? Now let me ask you this. Does this have an absolute minimum? No, how come? There's a bubble, okay? That is the lowest point, but it's undefined, so there is not one, okay, like that. Does it have an absolute max? Yeah, this is a definite point, so that also would be an absolute max. So pay attention to whether the function's defined there, because if it's undefined at a point, then it's not going to be a minimum or a max at all. All right, everybody okay with that? Okay. The concept behind this is pretty simple, but just pay attention to the little details of this. Okay, so now what I'm going to transition to next is symmetry. You're going to talk a lot about functions and behavior of functions, kind of first of all. This is stuff mostly you do in your head. All right, so let me talk about this example right here. This one would be this, and there's something that I'm going to put on here. I'm going to put a couple of points, like that is the point 3, 1, and this is the point 3, negative 1, like that. Okay, and I'm going to find one more point because I'm wanting to illustrate something. That looks like that is the point. Hold on, I did that totally backwards. That first point, let me fix that. Okay, this is the point 1, 3. And this is the point 1, negative 3. Oh, that wasn't where I was thinking on that. So we got that, okay? Now I'm going to write one more point because this is kind of important. This right here is the point 3, what is that? 1, 2, 3, 4, 3, 4. And then you have a point down here, 3, negative 4. Okay, now I'm wanting to show you something on this. So this is symmetrical about the x-axis. All symmetrical about the x-axis means is if you folded over your x-axis, they would come together, right? Well, what I want you to see is what happens. Something's the same and something's different, right? So if you're symmetric about x, x is the same, but y is opposite. That should be logical because if y is opposite, it moves it over the x-axis, right? Okay, same thing here. X is the same, y is opposite. So what you have, anytime you're symmetric about x is the same, y is opposite. Okay, that's what that means, and you need to get that in your mind instead of just being able to look and see whether it's symmetrical or not, okay? If you're symmetric about the y-axis like this, I'm going to pick locate a couple of points on here. Like this point here is the point 2, 4. Now this point over here is the point negative 2, 4. So what you would find is this is symmetric about at y. So if you took this and folded it across y, then they would match perfectly, right? That's generally pretty easy for students to see, but what happens if you're symmetrical about y, what's the same as y, but x is opposite? Does that make sense to you? Okay, that's what reflects you over the x-axis, is just make x the opposite. So that's how that goes. You want to get that kind of in your mind that you have the same y, but you have opposite x's. Okay, that's how that goes. Okay, those are usually easy for students to see. What's symmetric about the origins, usually a little harder to see. So let me write a couple of points on here and show you this. I'm going to pick like this point looks like that's the point 3, 3. Okay, well, if you look at this point over here, that's the point negative 3, negative 3. So what's symmetric about the origin means is this. Every point on the graph, if you have an opposite x, you also have an opposite y. So they're both opposite. Now the way this goes, and you can imagine in your mind, if you folded over x then fold it over y, can you see that they would come together and match perfectly? Fold over that way. Does that make sense? Okay? So if it's symmetric about the origin, both things are opposite. Okay, that's what you want to get in your mind, because of the next thing we do is once you get that in your mind, then it's easy to do this symmetry test that we're going to do. Okay? All right. So these things we're just going to identify and just kind of do this together. How is this number 8 symmetric? That's symmetric about y. Okay, so if you folded over the y-axis, they come together. Okay, that's what that means. Okay, how about the next one? If you study about polar coordinates and graph, which we'll do a little bit end of the semester, we'll do that. What is that? That's about x. Okay, good. So that's symmetric about the x-axis. Okay, how about this one?
Origin.
Yeah, that's origin. Origin's always harder to see, so think of it as just kind of going like this. Fold over one axis and then the other. So if you fold over there, then down, they do come together. Okay? And what will always happen is, like, aren't those points right there just total opposites, both x and y opposite? Okay, look at this point here. X's are opposite, y's are opposite. So every point's that way. So if you don't see the origin symmetry, just pick some points and see if they're x and y are both opposite. So that would be origin. How about the next one?
All of them?
X, yeah, I think maybe all. Okay, it's certainly symmetrical about x. Y, that's symmetrical about y. How about the origin? Yeah, if you fold over x, then fold over y, they come together. So that is all of them at the same time. And just as an example, if you're ever in doubt, just pick a point. That looks like that might be the point 1, 3. This point right here looks like -1, -3. And every point has that origin symmetry. Both are opposites. Okay, everybody with me there? Okay, all right, how about the next one? That doesn't look symmetrical at all. So that is none. That doesn't have any symmetry at all. Okay, all right? Or is it, oh, that might be origin. Hold on, that might be origin. What do you think? Yeah, okay. So sometimes it's not easy to see, like this point here and this point right here. That I can't even tell what those numbers are. I think that's maybe 1, 3, 1, -3. So does every point have that kind of structure to it? Yeah, that looks like origin. At first glance, it looked to me like it might be none, but that's what that is. All right? All right, everybody okay? Okay, all right. Okay, so next thing I'm going to look at is the even and odd function. And we're going to go over this just a little bit. So an even function has this type, basically a function's even if, what happens is if x is opposite, y stays the same. One of the best ways to learn this in Word is an even function. Every time you have an opposite x, y does not change. So here's an example. If you had the point 3, 6, what's going to happen is you'll have the same y when x goes to negative. So you might fill that in. So 3, 6 becomes -3, 6. Every point on the graph will have that feature to it. Okay? All right? And then we have an odd function. An odd function says if x is opposite, then the function's opposite. Okay? And you want to understand this terminology on this. This is changing x to opposite. Putting the negative in front of the function is changing y to opposite. So what would happen on this is you would change the -4 to what? +4. You would change the 9 to what? -9. Okay? So what basically in words, the best way to kind of look at what a odd function is opposite x gives an opposite y. So this would end up becoming on here 4 and -9. Okay, like that. Okay, so here's kind of what happens. If you have an even function, okay, take a look at, here's an example. You have 2, 5, that would become -2, 5. How is that symmetrical? How are those 2 points symmetrical? Same y, opposite x. What does that tell you? Which axis? Y. Okay, so even functions are symmetrical about the y-axis. Okay, all right? Here's an example of an odd function. Say that you have the point 1, 6. That would change to -1, -6. What is that? That's origin, right? Okay. So you're kind of relating those symmetries like that. So odd functions are symmetrical about origin. even functions are symmetrical about y. Okay, it's the same basic idea. Okay, any question about that? Okay, all right. Now what we're going to do is we're going to test functions and see if they're odd or even. So I want to kind of get you, make sure that you're doing this correctly on here when you do this, okay? All right, so basically what you do is, what you do when you're looking at this with an equation, you replace the x's with negative x, and then here's what happens. If you get the same as the original, then it's even. If you get the opposite of the original function value, that's odd. If neither of those things happen, then it's going to be neither. Okay, and I'll show you kind of what we mean by that. We're going to look at some graphs, and then we're going to start transitioning into I give you a function, you figure it out without graphing. Okay, that's what we're after. Okay, all right. So let's take a look at this one. Okay, what does this look like to you? Remember, even is symmetric about y. Odd is what? Symmetric about origin. How does that look symmetric? About y. Okay, so that's going to be symmetric about the y-axis. Okay, so it's an even function, and again, you can write on there, it's symmetric about the y-axis. Okay, that's what you're looking for on even and odd functions, is how they're symmetric. That's the simplest way to look at it. Okay, all right. Okay, next page, let's take a look at this one. Even, odd, neither, what do you think? It's odd. Why is it odd? It's symmetrical about the origin. Okay. Okay, and the way I kind of look at this is like this. If you don't see it clearly, just pick a couple of points. See, those 2 points right there have an opposite x and opposite y, don't they? That's it. That's what you look for. Every point's like that. Okay. How about this one? That's odd also. Okay, same reason. Like that point, those 2 points have opposite x and opposite y, and every point on the graph has that feature, so it's odd because it's symmetrical about the origin. Okay? All right? Okay, let's scroll down and do the next one. What do you think on this? Yeah, that's nothing. That doesn't have any symmetry at all, so you can just put on there that's no symmetry. Okay? So odd goes with origin, even goes with y-axis. Okay? Otherwise, it's neither. Okay? All right, any questions on that? Okay. Now, this is the part right here that students a lot of times don't do so hot on, is this right here. So this is what you need to pay attention to, how you show your work on this problem. We're not going to do this by graphing. So what you want to do is this. We're just looking at a function I give you, and we're going to figure out what it is. So I'm going to just write down the original function is f of x is negative 9x squared minus 6. So what you're going to do is you're going to get a new function out of this. So here's what you do. You do f of negative x. Now, if you're doing f of negative x, all that means is go to the function I gave you, where you see x, replace it with a negative x. So you would want to write on your paper negative 9 times negative x squared, and then minus 6. You always start your test by doing this. Okay? Now what we're going to look at is if it turns out to be the same, that means even function, because opposite x gives same y. If it turns out to be the opposite of the original, that's going to be odd. Opposite x, opposite y is going to be odd. Otherwise, it's neither. What do you think? Yeah, this part right here is definitely, when you square that negative, just takes you back to x squared. So you get 9x squared minus 6, so that's equal to f of x. So what you're trying to show is that f of negative x is equal to f of x. That's what makes it an even function. That's the idea. And that's how you want to do that on your paper. You want to show that, show that you're doing f of negative x, and then see what your result is. Everybody okay with what I did there? Okay. What does the graph look like down that anyway, from your background? What kind of graph is that? Yeah, that's a parabola that's upside down, and it's actually down 6. So it's going to be symmetrical about the y-axis, okay? All right, let's take a look at this one. So I'm just going to write down the original. You don't have to do that. I'm just kind of showing you that you're comparing the result to the original. So we're going to do that. Okay, that's the original. Now the new function, we're going to do f of negative x, which basically means this. Everywhere you see a x, in your function, just replace those with parentheses negative x. So we're going to have, be careful, that will be negative x in parentheses to the third, and then the denominator is going to be 7 times negative x squared minus 3. If it's the same, it's even. If they're opposites, it's odd. Otherwise, it's neither. Okay, let's look at the numerator. In your head, what would the numerator be?
Positive.
Okay, yeah, be positive, because that would be negative, right? If you take a negative number to the third, it's negative. Then negative gives you positive. So that numerator is going to become positive x to the third. What's going to happen in the denominator? It just goes back to x squared. If you square a negative number, it just becomes positive. So that's 7x squared minus 3. Now, what you want to do is you want to look at what I gave you and look at what we ended up with. They're not the same, right? Are they opposites? Yeah, okay, on a fraction, what has to happen on a fraction is either the numerator or the denominator is opposite. So for instance, if you have something like this, I mean, how are fractions opposite? What's the opposite of 2/3? Negative 2/3. So just the numerator needs to, or the denominator needs to be opposite. So that would be an odd function. You would write that as negative f of x. So what we ended up with was f of x, but it was the opposite, so that's an odd function. That's the way I want you to write that on your paper. Write your steps out like that. Okay, you're showing a demonstration of why it's odd. Okay, everybody with me there? Okay, all right. Okay, let's take a look at these two. Now, what I'm going to have you all do, just go ahead and I'm going to give you a couple of minutes to do these yourself and just try to do exactly what I did and see what you come up with. But see that you can write it down correctly, okay? All right, I'm going to walk around and see if you're doing okay, all right? Sometimes that's the only way I can make sure students are doing what they're supposed to do. But I also like to kind of look and see how students are writing these things out on their paper. Try to follow that procedure just like I'm doing here, and then that will help you get your answers. It's either the same, opposite, or neither. So you're going to either end up with f of x, negative f of x, or none of that. That's good so far. Okay. Now we're trying to do this, at this stage without really worrying about any graphing or anything. Yeah, that's fine. You want to follow on here. Do 17 also. Just do the next two so I can make sure everybody's had a chance to do a couple of these in class. So a lot of times students don't write these down very well. They get the right answer, but I have no idea if the students really understand that. Yeah, that looks good. That looks good. Okay. So now, if you're not writing these out the way I'm trying to show you, correct yourself on this. So this one, and you don't have to write the original function. I'm going to go ahead and write that because we're going to compare the result to the original. Okay. All right, so what you want to do on your paper is write what f of negative x is. Okay, if you didn't do this, write it exactly like that. That'd be negative 3 times negative x over absolute value of negative x. Okay, what that becomes is the numerator becomes 3x. What does the denominator become? Hey, when you take an absolute value of a negative number, it just stays the same, right? Now, it's still an absolute value. You cannot take that out of absolute value. Okay, it's just saying, hey, what happens if you have the absolute value of negative x, it really means this. And that's just 1 times absolute value of x. That's how you treat an absolute value of a negative number. All right, so what did you come up with for your result? That's odd, okay, because that's the opposite, isn't it? So what you want to write is negative f of x. If you didn't write that, put that on there. I want to see that on there, so that's an odd function. That's what you're trying to prove. That's how you prove it. Okay, everybody solid with that? Okay. All right. Next one. Let's see. We have f of x equals 4x to the third plus 6 Okay, you want to write it out like this. F of negative x is 4 times negative x to the third plus 6. Right? What you would get here is this would now be negative 4x to the third, right? Because if you cube a negative number, it becomes negative, like that. Well, what do you think? Is that the same, or is it the opposite? What do you think? What did you put? Odd. Are you sure?
Neither.
No. Okay, here's what you got to look at. Tell me what the opposite of that whole expression would be. Negative 4 and negative 6, right? The opposite of an entire polynomial would be the signs would be changed. That's not opposite. Hey, the 4 is opposite, but not the 6. That's a neither. Okay, that's not the same, so it's not even, and it's not opposite. Okay, so that one would be a neither. Does everybody understand that? Okay. Okay. So on the opposites, just make sure you understand what's meant by the opposite of the expressions we're given. Okay. All right. Now, one more thing I want to look at before we take a break. I do want to work a little bit on this difference quotient idea, and we'll kind of start a little bit before we take a break here. And this is something that if you're going to take calculus, you're going to do a bunch in a calculus class. In pre-calc, we want to give you the idea of how to work out this expression and kind of prepare you for calculus. So this thing right here is called the difference quotient. We're not going to talk about what it means yet. So what we're going to do is just take a function I give you and put it in what we call the difference quotient. Now, the way I teach this, a lot of times students have never done this, so there's sometimes takes a little time to catch on to how you set it up. Just write down this part right there. Write down what the difference quotient is. That's f of x plus h minus f of x over h, okay? Now, what I like students to do on this is just put like a set of parentheses here and a set of parentheses there, okay? All you're doing is you're doing f of x and then f of x plus h, okay? And you can process it this way. F of x is what I gave you, correct? So put that 2x minus 9 in there. That's what that means. That does not change. Okay, so the 2x minus 9 goes like that. That's always the same on these problems. Now, what does f of x plus h mean? It means take x and change it to x plus h. So what's going to go here is the same thing, but it's going to be 2 parentheses x plus h minus 9. So if you set it up that way, then we're only making one slight twist. This thing right here becomes x plus h, and make sure that's in a set of parentheses, then the minus 9's the same. Everybody see what I did? I've been teaching this for years, and this is the best thing I've come up with. Put f of x, first parenthesis, just change the x to x plus h. That's it. Now, what you're going to do is you're going to simplify this. Now we're just going to do basic algebra. Okay, so we're going to do like a distributive property there. So that's 2x plus 2h minus 9. That takes care of that. Now, again, you're going to distribute this negative through, so that will give minus 2x, and then a minus 9 is a plus 9. So be sure that you're really, really careful about doing that. All right, everybody with me there? Okay, now you're going to notice when you do these different quotients, a whole bunch of stuff is going to cross out. Those cross out, those cross out, so you're left with 2h over h. The h's cross out, so the result is 2. Okay? How many people took calculus like in high school? Okay, let me ask you calculus too. So, can you tell me what the derivative of this is? 2. Okay, that's what that means. Now, when you're a calculus student, you end up doing a limit of this as h goes to 0. So those of you who have had calculus before, you can tell you're right by doing the limit of your answer and seeing if it's the derivative that you learned. You see what I mean? So the rest of you don't need to worry about that. You just need to know how to put that in a difference quotient and put that together algebraically. Okay, next thing I'm going to do here, I'm going to go ahead and do 19. Then we're going to set up 20 together, and then I'll give you a little time to see if you can finish up number 20. Okay, on 19, go ahead and write it like this. We're going to just write down the difference quotient. That's f of x plus h minus f of x all over h. Okay, so we're going to go ahead and get that set up basically. Okay, and then we'll go through this one together. Okay, what I usually tell students to do is just, you can put 2 sets of parentheses or brackets all over h. before you build it and get it set up. Okay, it's real simple what you do. What goes here? Whatever I give you, right? What goes here? You change the x to what? X plus h, that's the only difference. So I say start there. Always put what I gave you. The difference quotient, you want to put the 3x squared here. Now the f of x plus h just means write the same thing, but where you see an x, replace it with that. Okay, like that. X will be in parentheses x plus h, all right? Everybody solid with that?
So the power of 2 goes outside of that?
Absolutely, yeah, because the x gets replaced with a whole expression x plus h. So that's real important. Okay, now we're going to go ahead and crunch this one out. So the first thing I'm going to do is we're going to do this. And you can either foil this or you can do it in your head. I've gone through how to do this in your head. So I'm going to go ahead and just foil this. So that's x squared plus xh. Inside term is another plus xh. And then the last term is going to be plus h squared. So that's going to give x squared plus 2xh, because you have like terms, plus h squared like that. So just kind of get that out of the way to start with. All right, now what I'm going to have from here then is I'll have, the numerator is going to be 3 times x squared plus 2xh plus h squared, like that. So we've done that in FOIL. And then we're going to have minus 3x squared like that. Okay, now we're going to go ahead and crunch out the algebra on this one and see what we get. Okay, all right. So what I'm going to do next is I want to do a distributive property here. You want to go ahead and do that. So that's going to give you, in the numerator, 3x squared plus 6xh plus 3h squared. And then you're going to have a minus 3x squared there, all over h. Okay, putting together like terms. Now, what do you notice happening in the numerator? Something cancels. It always will on these problems. So I do want to point out that what will happen on these things is you'll have h's in there. You're always going to be able to make that h go away. Always, no matter what problem I give you, that h ultimately is going to cross out at the end for what we're going to do in this class. So what you want to do next is you want to factor this thing out. Okay, you can factor and just take an h out. You don't need to take anything else out because you want it to cancel with that h. So take an h out of the top. You'd have 6x plus 3h like that, okay, all over h. And then your answer to the problem would be 6x plus 3h. And those of you who have been in calculus, I'll show you, the calculus students, how you can tell you're right. Okay? Does anybody have a question what I did with the algebra on that? Everybody feel okay? Right? Okay, those of you who took calculus, tell me what the derivative of this is. 6x, am I hearing you 6x? Okay. What happens if you let h be 0? You get 6x? Yes, okay. If you've been in calculus before, you've actually learned how to do this, but you would have to let the h be 0 to check your answer. For this class, no, don't do the h equals 0, just leave it alone. That's the idea. Okay, now what I'm going to do on number 20 is, you're on your own on this, so work on this. Go ahead and you can write that problem down, see what you can get. I'll walk around and give everybody a chance to do this one, okay? And you can compare answers too once you get that. Those of you that are calculus students, you might be able to tell that you're right. I'd like you former calculus students to be able to do that, okay? So go ahead and work on that, then we'll take a break here in just a minute. And really, once you get it set up, there's a lot of basic algebra. You FOIL, collect like terms, but at the very end of the problem, you should be able to make that h in the denominator go away. That's the basic idea. I'm just going to kind of see how you're doing. That should be good. Have you been in calculus before? Oh, okay. I can tell you're right then. Okay, so that's good. So if you got, if you can FOIL and collect like terms and stuff and get it set up, it'll be okay. And in pre-calc, this is about as complicated as it'll get. I mean, if you can do this problem I'm having you do right now, you should be fine. We're not going to spend time going over the ones that are a little bit harder that you might do in a calc class. I'm just trying to get everybody going with the algebra. Okay, so you squared it out. I see you're forgetting about your 6x. No, you're okay. I didn't see that. You just keep going with that. So you'd have that, then you would have 6x plus 6h, and then plus 20. Yeah. Okay. So you got to do that. You have it set up right, and then you can take it from there. I think that's right. Is that what you got? Did you get the same thing he had? Have you had calc before?
I know.
Okay. All right. Okay, just you want to go ahead. Don't forget about your 6x. That's going to be 6 times parentheses x plus h. I can't tell if you have it on your paper. Yeah. So you're going to have x plus h squared plus 6 times x plus h plus 4. In that first big parenthesis, then subtract the function. Okay, I think I've seen that answer all right. You're not quite getting that right. Look at what I have on the board. In that first bracket, I'm going to have x plus h squared plus 6 times x plus h plus 4. Make sure you got it set up right. Now, see, that looks good. Well, you got that set up good. I'm missing one more detail. See how you have that leftover 6h? You forgot about it. So you need to do that. Right track. Oh, great. Now I think you missed something. Oh, there we go. Okay, thank you. Okay. All right. All right. I missed one little thing. I'm having a hard time seeing on the paper. Sorry. That's so tiny. Yeah. Make sure all that's worked out good. Multiply it out good. I think you're on the right track. I think you're on the right track. All right, tell me this. How many of you got 2x plus h plus 6? 2x plus h plus 6. Now, those of you who are calculus students, tell me what the derivative of that is. 2x plus 6. Okay, so if you take that 2x plus h plus 6 and let h go to 0, you get the derivative, right? Okay, so that'll help. The only thing that I'm seeing with some papers here, kind of writing tiny and small, you can't really see what's going on. So there was a few of you that didn't quite set this up right. Here's f of x, and then all you're going to do is change the x's in that f of x to x plus h like that. Write it neat like that, okay? Now, I'll go ahead and do this real quick, and then you can, if you didn't get the right answer, you can see where you went wrong. First thing I'm going to do is I'm going to do all of this, most of that in my head. Okay, so I'm going to FOIL out the x plus h, okay? We already did that. That's x squared plus 2xh plus h squared. That's what that is. Now I'm going to distribute, so that's going to be plus 6x plus 6h, and then plus 4, like that. Okay, now I'm going to distribute the negative through this, so that's going to be minus x squared minus 6x minus 4 all over h. Okay, so if you didn't get the answer that I'm going to get, you got to make sure that when everything's multiplied out, that's what you have. Okay, then what we'd have from here is that would cross out, the 6x would cross out, the 4 would cross out. And then what I want you to pay attention to is see everything that's left over has an h in it, doesn't it? So that means you can factor h out, then it'll cancel with the h at the end. So this would look like this. Once you end up with this, take h out, you'd have 2x plus h plus 6 all over h crosses out, and then your answer is 2x plus h plus 6. That's it. Looks like most of you got that okay. If you didn't get it right, just check your arithmetic and see where you went wrong. Right? You guys feel okay with that? to start with? Okay. Now that's probably as advanced as we do on this in this class. If you take calculus, you'll work with radicals and complex fractions and stuff like that. But on pre-calc, if you can get a quadratic, okay, and a difference quotient, that'll be fine, okay? All right, so any questions? So what we mean by a piecewise function, and you don't need to write these graphs down, it's just when you graph a piecewise function, there's just different pieces defined on different intervals. So you might have like 3 different graphs like you have here that maybe they don't connect. Or you might have 2 graphs like this, and then they're 2 different functions, but they do connect in a certain way. So that's kind of what piecewise functions tend to look like. If you're a calculus student, you'll work with piecewise functions quite a bit, and we use piecewise functions to model different things, different concepts and everything. So what I want to do on the next page, you need to write down 22 and 23, and let's focus just on what a piecewise function looks like and how we evaluate this. Now this is an arithmetic problem on 22. So you're given the piecewise function f of x. The first piece is negative 3x minus 2 when x is less than 1. And then the second piece is negative 4x plus 4 when x is greater than or equal to 1. Okay? So actually what you do is real simple. If you're finding f of 1, you're going to plug into this one. How come? Because if x is greater than or equal to 1, you plug in there, right? Okay? This is f of 0. You're going to plug that into this one. Why? Because 0 is less than 1. So you look at that condition. F of 2, where does that go? The bottom one, like that. So basically, when you look at that inequality, that will tell you which function to plug into. All right, so let's write down the solution on this, and this will be easy arithmetic. F of 1, you're going to plug into this bottom function because x is greater than or equal to 1. So that's negative 4 times 1 plus 4, so that's equal to 0. Okay, you just got to know which piece to plug into. F of 0, do you plug into top or bottom? Top, because 0 is less than 1. So you would say f of 0 equals negative 3 times 0 minus 2. So that would be negative 2. Okay, that's how that goes, right? F of 2, top or bottom? Which one? Bottom, because 2 is bigger than 1. So you're going to go like this. F of 2 is just going to be negative 4 times 2, and then plus 4. Okay, that would be negative 8 plus 4, so that would be negative 4. All right, so you got to know how to evaluate the function depending on which piece you're doing. Everybody with me there on that? Okay, all right. So this one says this. When x is anything but 3, you plug into the top. But if x is just 3, you plug into the bottom. Okay, so that's another way to write a piecewise function. So if x is 3 on g of 3, on this one you're going to plug into the bottom. And that's the only time you use that function. So that would just become 3 plus 1, so that's equal to 4. Plug into x plus 1. Okay, g of 4, what do? You plug that into the top. And if you do that, you would have g of 4 would be 4 squared minus 5 over 4 minus 3 like that. Okay? And that looks like that would give you 16 minus 5 over 1. So that looks like 11 over 1. So that's equal to 11. So that's, you want to get comfortable with what the meaning of a piecewise function is and how to evaluate. Does everybody understand what I just did there? Okay. All right. One thing you'll do in a calculus class, you'll do limits with piecewise functions. So you want to clearly know what that inequality means. That's important. All right, so the next thing we're going to do is we're going to do graph. And the graphs, students just hardly ever do a good job on this. If I give a test over graphing a piecewise function without a calculator, it always seems like half of the students miss it because they miss kind of a key detail on this. So I'm going to show you this way. There's more than one way to do these, but I like to have students just do tables of values because it's the safest way to get students to do this the right way. So you want to write down, you have the piecewise function f of x is x minus 3 if x is less than 1, and just 5 if x is greater than or equal to 1. We're going to do a table of values. So we're going to start by doing the first piece. So we're going to do y equals x minus 3, and we're going to make a table of values on this. Okay, like this. Now here's what you got to know. All right, so where do you begin your x on this problem?
0.
Actually, you begin at 1, because that's where it comes to an end. Even though there's not an equal to bar, you want to go ahead and do 1 because you're going to have an endpoint there of some sort. So what I like to have students do is this. You are choosing numbers that are smaller than 1. I would put a 1 there, but because there's not an equal to bar, that means it's excluded, so it means that endpoint's going to be an open bubble. Okay, that's what it is. Now what kind of numbers do I use? Just whatever I want that's less than 1. Let's just keep it simple and just do a few like this. Let's just do that. Now this is a line, so now we just evaluate. So we plug into x minus 3. So we're going to go 1 minus 3 is negative 2, 0 minus 3 is negative 3, and then negative 1 minus 3 is negative 4. Okay, so that's going to go like that. Okay, start with 1 as your barrier, and then pick numbers below. Okay, now go ahead and plot those points. If you don't have your printout, just kind of sketch a graphic and just be a sketch. So we've got 1, negative 2. Now that's going to be an open bubble when you go to 1, negative 2. Then you have 0, negative 3. Then you have negative 1, negative 4. And that goes on forever like this. Now let me show you what students do all the time. It drives me crazy. Students want that to just go on forever. Why does that not go on forever? Because that's what it says, right? If x is less than 1, that's your graph. When x is 1 or bigger, then you go to the other graph. So you change. Does everybody understand that? That line stops there. All right, that's important. And that open bubble is because of that excluding that 1. Okay? Now what we're going to do, now you can bypass the table of values. I just like to teach it that way at this level. Because, you know, students, if they just follow this, tend to do pretty well. So this is y equals 5. All right, what is the first x value you need to use? 1. And this time it includes it, so we're going to do a solid dot when we graph it. Okay, that's the only difference with that. You got to use a 1 on both, but one's open, one's closed. And then you're going to pick numbers bigger than 1, just like maybe 2 and 3. But y is always 5. That's going to give you a line that is horizontal. Okay, so when you graph this, then you go like this. Graph 1, 5. So go over 1, 1, 2, 3, 4, 5, and put a solid dot there, and then 2, 5, 3, 5, and so forth like that. All right, now that's your piecewise function. Here's what I see students do all the time. They want to make that go on forever and that go on forever. Do you guys understand why it doesn't? Okay, here's the other thing. Remember, this is a function. Does this pass the vertical line test?
Yeah.
Yes, okay, even right here, even right there, it goes through 1 point. Okay, but if you made the lines go on forever, it wouldn't be a function, right? So remember, you are graphing a function, so make sure it passes the vertical line test. All right, do you guys have any question about what I did there? Okay, yes?
So why did you get negative 2 if you can't plug that into your equation?
Okay, well, I plugged into here. I took the x, 1 minus 3 is negative 2. Then I plugged 0 minus 3 and so on.
It says if x is greater than 1.
Okay, but you need to get the endpoint of that. That's one place where a lot of times students are confused. You're going to go all the way to 1, but an open bubble. So see, if you started like at 0, then you'd have a little gap there. You need to go all the way to 1, but then use an open bubble. So always use that number on both, but distinguish between which one's open and closed. Does that make sense? Okay, because, I mean, really, technically, you could use 0.99999, right? Okay, so you need to know where that comes to an end. That's why you use 1. Okay? All right. So now, let's do this. Let's go ahead and write this piecewise function down. I want to do like 3 of these in class. So this is f of x, negative x plus 3, x is less than 2, and then 2x minus 3 when x is greater than or equal to 2. Okay, and again, I'm going to take exactly the same approach on this. We're just going to do like 2 tables of values. This is a good, safe way to learn how to do this. So the first piece is, we'll have x, and then we'll have y equals negative x plus 3. Okay, where do I need to start on this one with x? Is it open or closed? Open, so you got to go there. Now, what would be a good next number? 1, anything less than 2, right? Okay, just use like 1, 0 like that. Okay, but start with 2. Okay, now plug in and evaluate. So you would have -2 plus 3 would be 1. -1 plus 3 would be 2. And then 0 plus 3 would be 3, like that. So you got a line, but you're going to have an open endpoint like that. So if you plot those 3 points, you would have 2, 1 that's open, 1, 2, 0, 3, and then you only go to the left like that. Okay, so that's what that piece of the function would look like. Okay, all right, now we go to the second piece, and we're going to have an x column and y equals 2x minus 3. What's the first x value I need to use? 2. Opened or closed? Closed. Then pick bigger numbers. Okay, so now pick like 3, 4, and it's a line, so all you need is 2 points anyway to make a line, and then plug in. So you'll do 2 times 2 minus 3 is 1. 2 times 3 minus 3 is 6 minus 3, so that's 3. And then 2 times 4 minus 3 is 5. Okay, like that. And by the way, anytime you have a line, it's kind of nice to notice if you have a line, if x goes up by an increment, so that's going up 1. See how that's always going up by the same increment? Lines always work this. As this goes up in a pattern, that will go up. Right? Same thing here. That goes down a pattern, that has a pattern. So you're always going to see that, what we call linear pattern to that. So now what you want to do is just plot these points. So you got 2, 1, which is here. Now, isn't that the same point? What does that tell you if they're the same point? The graph connects, right? Okay, it just closes off that place right there. So that's a solid point now. It's no longer open. Then you would have over 3, up 3. And then you would have over 4 and up 5 like that. So actually it connects because those 2 endpoints were the same. So either they connect or they don't. If they connect, it closes in the bubble. Does that make sense? Okay. All right. So that would be what the graph of that piecewise function looks like. Now, it's simple arithmetic when you get right down to it, but be sure you make your tables correct. All right. Okay. Let me go to the next one here. And then I'm going to do one more piecewise function. Write this down. This is the other thing I want you to know how to do. You could have 3 pieces. You could have as many pieces as you want. We're not going to go beyond 3 just to kind of get the idea. So your first piece is 4. Second piece is absolute value of x. And then cube root of x. And they're defined on these inequalities like that. I'm going to take exactly the same approach on this. I'm just going to take table of values just to be safe. So I'm going to do x, and I'm going to do y equals 4 like this. Okay, now this is a line. If you graph y equals 4, it's horizontal, right? All you need is 2 points. So what I'm going to do on this is I'm going to use these endpoints. So I'm going to use -4, and that's going to be a solid dot because it's less than or equal to. Then I'm going to use -2, and that's going to be open. Now you can fill in other numbers if you want to, but you don't have to. If you know it's a horizontal line, all you need is 2 points anyway. So that's going to be 4 and 4 like that. Okay? Same thing here if you went ahead and did like points between those. So like if you use something that's in between like -3, you would still get a 4. Okay? So now what I'm going to do is just graph these points out. All right, so I've got -4, 4, and that one is a solid dot. And then -2, 4 would be, it looks like an open bubble like that. So from -4 to -2, you have a horizontal line. Okay? All right? Now let's move to the next one. Okay, the next one you have x, and then you have y equals absolute value of x. All right, so the second piece we're going to go from, we're going to start with -2. Is that going to be closed or open, the -2? Closed. How about the 4? Open. And you need to pick some points on this. So -2 is closed. Then let's use a number in between -2 and 4. So let's use like -1, 0, 1, 2, 3, and 4. Now I'm going to use more dots on this because for your background, I hope you remember absolute value is the V shape, kind of, okay? So if you're going to get that accurate, you need to use a lot of points. If you know it's a line, then all you need is 2 points. So again, I'm just going to do absolute value. And of course, all this you can do in your head. The absolute value of -2 is 2. You're just doing the absolute value of each x value. And absolute value is always positive, so you can do that real quick. Okay? And then again, the 4 was open like that. Does that make sense, what I did? Okay? Now you just want to plot those points and then have a solid on the first and an open on the last. Either they'll connect or they won't connect, and we'll find out as we do that. So the first point is -2, 2, open, -1, 1, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and the 4, 4 is open. So see, you'd have that part of that V shape like that, like you would expect, okay? All right, then the last thing we're going to do is one more table of values. We're going to do a cube root. So we have x and we have y equals cube root of x. Okay, we're going to start with 4, and that will be closed, and then we'll go all the way to 12. Now what I'm going to do on this, I'm going to go all the way down to 12, and 12 is going to be also closed, so they're both closed. Now I'm not going to use just any number. You're going to get a bunch of decimals on this. You can do this on your calculator. So like if you did the cube root of 4, there's not a number you can think of in your head. You multiply out 3 times, it gives 4, right? It's a decimal, so I could take my calculator, and let me show you this just in case you don't know this on your calculator. So on the TI that I'm going to use, the math button is where you find the cube root symbol, right? You know, write down a note if you need to. So if you go math, you should see the cube root on option number 4, okay? So I'll just do cube root of 4, and then use a decimal on that. So I'm just going to use, like on that, that's about, we'll just say 1.6. Then I'll go to the 12. So if I go math and then go cube root of 12, like the same thing, I'll get a decimal on that. Whoops, I didn't mean to do that. So I'm going to go math and option 4 and cube root of 12. Okay, so that's going to give about 2.3. Okay? All right, now, and that's good enough. Now, what I want to ask you guys, though, is between 4 and 2, or 4 and 12, what's a number that has a cube root? 8. 8 does. The numbers that have cube roots are like 1, 8, 27, 64, 125. So all I'm going to do is I'm going to put 8 there. I mean, you can do more if you want to, but you'd have to crunch that on the calculator. Cube root of 8 is 2, like that. Okay? Then from here, we'll go ahead and just do a graph. So we have over 4, up about 1.6, solid, just estimate it. And then 8, 2. And then finally, you'd be over, it looks like at 12 and a little bit above 2. So you would have it's not a line, it's a curve that's going like that. And it wouldn't go on forever. It would come to an end at 12. So I didn't quite do that right. So I need to have a dot on the endpoints like that. So that's how that goes. All right, does that make sense? Are you going to be able to do that okay? Students botch this up bad. I'm not criticizing. I'm just saying what I see all the time. Okay? Just crunch out individual tables and you won't go wrong. And just make sure that the graph does not go on forever. Is that a function? Does the graph I drew, does that pass the vertical line test? Yeah, okay. So if it doesn't pass the vertical line test, then you're messing up. So I always say at the end, make sure you got a function. Okay? All right. We're going to do one last thing to finish up this section, then we'll get a little bit into the 1-4. And we're going to do something on the graphing calculator. So if you did bring your calculator with you, just get that out and do this along with me. Be sure that you start bringing your calculator with you, because we'll do a lot of things on this. And sometimes students from high school have a great background. They learn more about it than I know. Sometimes students that haven't been in school in a long time haven't even learned some of this stuff. Graphing calculators came out in about the 90s, the 1990s. When I started teaching, they weren't even really, you didn't even use them as a teacher. So in the 90s is when they started coming out. What we're going to do on this is we're going to graph this on this interval, and I'm just going to show you how to find a max and min, okay, on this. So what you want to do with this is you want to press your y equals button and just put this function in. So just put this in your calculator. Go ahead and do that. So you have negative And remember, if you use a negative, use that. Don't use the subtraction key. I see students do that all the time. So that's negative 0.3 x to the third. That's your raised to key. X to the third. Be sure you bring that exponent down like that. Then you would put in plus 0.2 x to the second. You have an x to the second key that'll do that automatically. And then plus 4x. And then minus 5 like that. Okay? So if you haven't used a calculator in a long time, be careful about how you get those exponents in. Okay? Just put it in like that. Now, what you're going to do with this is you're going to set up your window. So we're going to go ahead and set that up. We're only interested from -4 to 5. We don't need to graph except between -4 and 5. So you press your window button. The minimum x is -4. The maximum x is 5, like that. And then you'll scale that by 1. The scale just means you're counting by ones from -4 to 5. Okay? Now, one thing I see students do all the time is they say, how do I know what to do for y? Here's how you know this. You have a table of values. So if you see that table above graph, if you go second graph, a table of values will tell you what your y's range for. So if you look at this table, we're ranging from 1.4, then we're getting all the way to -17.5. So if I was doing my y window, I'd probably use -20, and I would probably go all the way up to about 2. And that would give all my data, right? You guys see what I'm talking about? So that table will help you figure out what to do for y. These calculators have this zoom fit thing on it, but it's better to do it this way, all right? So what we're going to do on this then is we're going to go -20 to 2. So on the y, I'm going to do this like this. -20 for y min. Okay, and then I'm going to do the biggest thing I found was less than 2. And then I'll scale that by 1 or whatever you want to do. Okay, like that. So that's how you would want to get that set up. All right, everybody okay with what I'm doing? Okay. Now you press graph, and I'll show you how to find the max and min. Okay, so if you look at this particular problem, how many relative mins does it have? It has 1, right? How many relative maxes does it have? It has 1. The endpoints don't count, okay? So what we're doing is we're doing relative maxes on this. Now, what I'm going to do on this is now I've already written out on your notes how you get this if you don't know this. You don't necessarily have to write the keystrokes down. Let's start by doing the maximum. So here's what you do. When you have the graph, you go like this basically. You just go to the calc command like this. So you want to go second and then trace and get calc to come out. And then you go down to the one that says maximum. And then you're going to find what that max is. And you can get it precisely. So what you do is once you've done that, you get a left bound. And all a left bound means is just kind of get real close to that max, somewhere in there, and then press enter. Okay? There's not a specific place you got to get that. Just don't go beyond it. So just kind of close in pretty close. Press enter. On most calculators, a line will come up. That's a barrier. Then you want to get a right bound. So the right bound, I'm going to take my right cursor key and just move it until I'm convinced that I'm to the right of that max. I press enter. You'll see 2 boundaries, okay, like that. Then when it says guess, just press enter one more time, and then you're going to know you're doing this right because it's going to blink on that and tell you it's a maximum. So that point right there is your maximum. Okay, everybody see what I did there? Okay, so you have that maximum command that'll narrow that down for you. So let's just write down what we have then. So we have a max is going to be at, and I'm just going to round to like 2 decimals. 2.34, 1.61, like that. So that's your maximum, okay? Now, when we do the minimum, you start over again. So what you do is you go second, trace to get calc to come out. Now you go to option 3, which is a minimum. So you do that, press enter, and you do the same thing. Use your left cursor key to get to the left of where that minimum is, and just repeat the same process I did. This calculator on this is a little slow sometimes. Okay, so just get a little bit to the left of it, and then press enter. Now for a right bound, get a little bit to the right of it. Okay, press enter. Then press enter one more time, and it'll tell you you've got a minimum. When it says guess, press enter. So that relative min is going to be and I'll say on this negative 1.9, I'm going to round that to round that, and then negative 9.82 like that. That's it. Everybody got that okay? Okay. Now you'll do that a lot in this class, and particularly in calculus and stuff, you'll do this to kind of tell if you're right on things. It's a good way to check. Now if we do the interval on here, what you're going to basically find is you're going to increase from here to here. So increasing is going to be from this x value to that x value. So we'll increase from negative 1.9 until we get to 2.34. So that is increasing in that region there. Decreasing is going to be from negative 4 right there, okay? And we're going to use negative 4. We're not going to go to infinity because I gave you an interval until we get to this x value, which is negative 1.9. Then union, and then from this x until you're at the end of the interval, which is 5. So that would be 2.34 comma 5 like that. And it's an open interval. It's always open if you do increasing and decreasing. Get that in your mind. Okay? All right, that's just technology. I want to make sure that you're comfortable with your calculator and know how to do the tech okay. Everybody follow that okay? Right now on the notes that are on Canvas, the steps are on there. So if you're not familiar with that, just follow that and you should be okay.
What did you call that? Negative 4 and 5?
Those are endpoints of the interval. And the reason we don't have infinity on that is because we have a definite start and a definite end, because I gave you that as a part of the problem. So that's why you got to use that in there then. Okay.